So here we have to determine our models actually overfit models or underfit models. So how to determine through some simple calculations, how to determine this thing. So let's see. So how to determine in k nearest neighbor, how to determine the best k. We have seen just in previous lecture, we have seen by simple k fold cross validation or simple cross validations, or simple using the cross validations data. We are using the best k, we are finding the best k. So in this best k, we have seen this in the best k our model is not as overfit models, or it is not a underfit models. So it is simple, neither overfit model or nor it is a underfit model. We have seen this thing. Okay. Now the questions is here, say how can we be sure that we are not underfitting or overfitting? How how can we be sure that we are not actually underfit or overfit? How we can be sure about this thing? So let's see. So to confirm of our model is overfit or not overfit, how we justify our models is in one of our previous lectures we have seen this thing. Suppose we are calculated the accuracy, to justify our models. And how we calculated this accuracy? Simple. In numerator we have taken the number of correct classify points, number of correctly classified points, was correctly classified points, and in denominator we have taken the total number of points. We have already seen this thing, and the error is simple, the opposite of this accuracy. Means if our accuracy is, suppose let's take our accuracy is 0.93%. Let as an example. Then what will be our error? Suppose in this case error will be 1 minus accuracy, means accuracy error will be 1 minus 0.93, that is 0.07, means 7%, means 7% it is, or error is actually 7%. And what we are actually interested to do, we are interested to increase our accuracy value for a models, and we are interested to decrease our error value for a model. This thing we are actually interested to doing this thing, doing this job. Now if you just see our data sets, so our data sets, our having data sets is, if we take our having data sets a dn, then what we are doing in cross validations, we have to partitions this data in randomly. So in the train, in the cross validation, and in the test, we are doing this thing randomly. And to find our best functions, we have use only these two things, this, that is the train data and the cross validation data. In knn we have find best k. To find our best k, here we are using the cross validation data, and to find the train as our nearest neighbor points, we will see this thing. We have seen already this thing in a cross validation technique. Now how to determine the best case? Just if you just draw a picture like that, this x-axis is k-axis, and this y-axis are actually accuracy on the cross validation data, and here actually k is equals to 1, k is equals to 2, k is equals to 3, and up to k is equals to 8. This thing we have doing actually, and our accuracy on cross validation lines between 0 to 1, and we have seen these things. Our curve we likely this first we have increasing the accuracy, and after some time we have decreased these things, and the highest value of this accuracy we got our perfect k. Suppose let's take here our perfect k. Suppose let's take actually here is our perfect k. So this is the maximum value of our accuracy, and that's k is called the best k. That k is called the best k. Here is our best k, or simple optimal k. And in this k our model is neither underfit nor overfit. We have seen this thing. We have geometrically see this thing, but how doing this thing numerically? Neither underfit nor overfit. So always it is not possible to draw the curve and to find the best k. So how to doing this job? So let's see. And this test data we have taken as a unseen data. We have taken this test data as unseen data. And how it find the error? So we have find the error on our G cross validation is simple 1 minus accuracy of D cross validation. You have seen this thing. Now the accuracy on the cross validations, how to find accuracy? Actually, if you just remember this thing, if you just remember these things, we have taken the h point from our cross validations. We have taken for h point, we have taken the h point from the cross validation, from D of cross validations. And suppose let's take this point is actually, let's take our point is look like that, xi yi, look like that. We have seen this thing, I is equals to 1 for number of data sets in our G cross validation. And we have taken the h point as query point first. Suppose let's take our query point is xi, that's coming from here, and we will find its corresponding output from our models. We'll find these outputs from our model. Suppose let's take the corresponding predicted output from our models is yi, and we compare these things. If you compare these things to this output, actual output, that is yi, if conditions is true, then we have count as a correctly classified point. Then we have count it is a correctly classified point. And we have doing the job repeating we have repeating these jobs for each point on our cross validations. And sample by using this formula, we are find the accuracy of our models. We have already seen this. Now the thing is that we have find these things, everything is okay, but how the things is calculated? Just tell the main how to determine the numerically overfit or it is underfit, how to find this thing numerically. So let's see. Now let's see. So to before going to the discussion, so let's draw or let's learn one concept, that is training error. Till now we have not known what is actual training error. Now training error, what is training error? Okay, so training error is here what we are doing. Just if you just read remember these things, we are using here training data set for our nearest point for cross validation technique. Just I am just for simplifications I am taking here cross validations. I am not using the k fold cross validations. I am simple using the cross validation technique. We are using the training data sets at nearest point and using the cross validation data sets to find the best k value. Okay, to best k value, and according to this we are deciding what will be our actual functions, that is functions f k n, what will be the best k. We have already seen this thing. According to this thing we are using simple to these data sets, we are finding this value, what is our best k for this model. Now suppose let's take from this thing we got, suppose let's take from these two things we got, let k is equals to 2. So let t k is equals to 2, we got this from our cross validation data. So now the questions is what is the training error? What is the training error if we consider 2nn, means k is equals to 2 here, 2nn, if we consider k is equals to 2. So this is the big questions, what is the actual training error? So let's see. So suppose the same thing we are doing as previously, it's the same thing we have doing here. So here we are taking the for hxi simple training error, means we have, instead of find the accuracy, here we are what find the accuracy, we are here using the cross validation data. Here simple using the cross validation data to find the accuracy, but instead of using cross validation data we are using here training data to find our accuracy. So for hxi in dtrain, this is the main difference for cross validations error or simply a training error, or cross validations error and training error, between the training error in the sample accuracy. So if you got the accuracy, then you can easily got the error. Right? This is the simple subtractions of that. So actually training error means training accuracy is that we are instead of we have taken the point from cross validation data, we are taking the point from our training data to find the accuracy. This thing is called the training accuracy. And if you just calculate your training accuracy, then by simple subtracting from 1 this value, we can easily got our training error. So just see, first for h.xi in our dtrain, we have to find what? Find the two near nn point. Find the two nn point, means two closest point. And just here I have taken k is equals to 2. So to find the, for this I have taken the two closest point, two nearest neighbor points to xi, means that is actually these things is now for our query point. Taken the two nearest point to xi, that is taken from our dtrain data set. Okay, this is the first step we have to do. The second step, what we have to do? The same thing we have to do, means we have taken the majority vote. We have find the majority vote. To get the class level. Okay, simple. First we have decided instead of query point that we taken our cross validation data, we are here taken the query point as from the train data, and we have find the two nearest neighbor points from the xi that is taken from our x training data, and then find the majority votes to get its actual class, to get its predicted class level. Now it's find the accuracy. If this yi, that's corresponding yi, that point is taken, if this corresponding yi is actual is equals to our class level that we are finding here, this class level, this class level, this class level that we find here from this majority vote, actual our class level, then we accurate, we then return the accurate class level is accurate, then accurate return accurate, else we return the error. These things we have also previously seen, just I am just written these pseudo codes. Okay, I think you have understand this thing. So simple, this thing is so simple. Detrain simple, instead of cross validation data, here we are using to training data. This is nothing, this is the training error, actually this error. So detraining, instead of we are using training data. So this thing is same for or for every cases, but the main difference is, so here for find the accuracy, here we are using cross validation, here we are using for find the accuracy, or simple error, you can as you like, we are using the cross validation. But for training error, instead of this thing we are using the detrain data. Okay, I think it is clear, all of you. So this is called the training. Now the validation error, this is called the training error. Simple. Now the validation error, what is actually the validation error? Validations are these thing, both the same thing, just see the same thing, same algorithms, just instead of we have training for finding the accuracy, instead of our detrain data, here we are using the cross validation data. This is simple, or general accuracy or general error that we call, that we see already, that another we call validation error in another language. It is a general error. So in this here we are taking, if we just for training purpose, here we are using detrain data for training purpose, and here we are using the cross validation data to find its accuracy for its error term. Both the same thing, just instead of the train set for find the accuracy, here we are using the cross validation set to find the accuracy, until it is everything is the same. Now let's see the, I think the concept of training error and validation error is clear. Now let's, using these two things, how we will find the actual our model is overfit or underfit. Let's see now. So I think this will be better if we just draw a picture, then through the pictures it will be clearly visualized. I think this thing, suppose let's take this is our picture, and simple, this thing is our key axis, and here we have drawn the error axis. Okay, and it here k is equals to 1, here k is equals to 2, here k is equals to 3, up to k is equals to, let's take n, and our maximum error will be also 1 and minimum error will be also 0. between two this thing. Yeah. Now what we'll see, so we see that our cross validations accuracy, just if you remember our cross validations accuracy like on that. So if our cross validations accuracy look like that, cross validations accuracy means simply the validations accuracy or validations accuracy, or it is simply validations accuracy. If accuracy is like that, then error will be like its opposite directions, because accuracy is simple one, error simple 1 minus accuracy. If we take this k-axis and this is our error axis, then this thing will be like that. This thing will be like that. Okay. So here, when our error is minimizations, here we can find our best k. This point will be like that. Simple, this curve is called the cross validation error, validation error curve, validation error curve. Okay, this thing. So just same thing is draw here. We are drawing here. So our cross validations will be look like now this thing, this kind of. So first draw the training error. I think then it will be clear. So first draw the training error. So if you see, when we have taken k is equals to 1, then what actually our error term? So just see, just to draw this picture, I think it will be better if we just draw the data set first. Just to remember. So first remember this thing. Suppose let's take as the same example I am here that I have already previously taken. Suppose let's take this is our negatives positive set of data points. And let's take it is our negative set of data points. Okay, so if we taken some error here, here we have some misclassified point like that, here also some misclassified point like that, same things also occur here, same things also occur here like that. Okay, so if we taken k is equals to, suppose if here we have taken k is equals to 1, here we have taken some larger value than that. Suppose let's take k is equals to 5. Let's take k is equals to 5. So what is actually happening here, when we have see that this thing, if our k is equals to 1, then the curve will be like non-smooth curve. We have seen this thing like that. Like that curve we have got. But when k is equals to 5, then what happen in such scenario? Then our curve is look like that. Smooth curve. That easily draw through a 5-year or 3-year-old kid. We have already seen these things. Mean when k is equals to actually 1, then what happen? Then our training data are perfectly classified. Then or actually we have this thing, these neighbor points, actually these things coming from our train data, these neighbor points are coming from train data. And if we use k is equals to 1, k is equals to on this, if we just find its accuracy, if it's find its accuracy, then in such scenario we got no error, because these points are coming from the training data sets. These points are coming from the train data set. These points are coming from the train data set. And then our train error, then if we've taken train error, we have doing no mistakes. Okay, then in such scenario train error is actually approximate equals to 0. We have doing no error, no train error. In another language, here our train error is low. And in such scenario what happened? In such scenario if you just see, we have doing some mistake. our train error is not non-zero, means we have doing some mistakes here. If we just using to find its accuracy our d train set, then we can find in training sets our points look like here also some mistake, doing some mistakes, here also doing some mistakes. But actually what this is a classification, this is a classifier doing that this regions is positive regions and this regions is negative region. And if we take to justify these models, then our data sets will be this point it is misclassified. Misclass point here we got this point is misclass point. Misclass point, actually this data are coming from training data sets, so here we have doing some mistakes. So here train error is non-zero, we have doing some mistakes here. But if you just see here, if you just take a cross validation error, suppose on this data set, suppose let's take we are taking some cross validation point. Suppose let's take our cross validations point look like that already we have taken on previous examples. Suppose let's take our cross validation data here. Suppose let's take our one cross validations data is here. Let's take our one cross validation data is here, one cross validation data is here. The same, if you just same this doing the same thing, let's take one is here and one is here. Cross validation data, one is here, one is here. Okay, so for this case when we have taken k is equals to 1, then if we have just taken this curve, this non-smooth curve, then our curve will call that this point means this is actually our positive region and this is actually the curve on this curve, it is the negative regions. And when taken that our curve, our decision surface, this decision surface call this point actually a positive point. Positive point, and decision surface call that this point actually a negative point. This point decision surface call that it is actually negative point. So in such scenario we have doing some mistakes from our cross validation data. This is actually coming from the cross validation data. Okay, here we for cross validation data we have doing some mistakes. So here cross validation error is high. But here if you see, just here if you see this thing, here our cross validation point is saying just this side is actual negative. So we got what? We got this is a negative point, this is actual negative point. But here we have got is a positive point, and here we have got what? And this is a this point is positive point. But opposite thing we have to see in this graph. So here our cross validations point error is low. Here cross validations error is actually low. We are doing this. So when just see this thing, when we have doing k is equals to 1, then our training error is approximately 0, and if we just increase the value of error, then train error increased. If we increased k value, if we increased the k value, then our train error increased. Then our train error increased. Okay, and if we increase the cross validation error, it is initially increased, then after some time we have seen that it is decreased, and then after when we going to it tends to end, then it is again increased. So then increase, just say this thing, k is equals to 1 2 3 dot up to n. So we have seen that our cross validation error in such in some regions, in some regions our cross validation error in cross validations error in some regions is high when we have taken, that is from overfitting. This in these regions are actually overfit model, and in near of end point it is actually our underfit model. Here also high, but also cross validations error here also high, both the cases. But in middle value in somewhere here in middle value our cross validations error is low. We have seen this thing. We have seen this thing here. Okay, so just the same thing is drawing here. We have drawing here. So first draw our cross validations here. Cross training error. Training error, if we increase the value of k, then training error is increased. Just it is 0 to it is increased. This cross validations error increased. Like that, we got our graph. This kind of graph we have got. We will got from our training error. This thing is called the training error graph. Training error graph. Okay, now we have seen that in cross validations graph, cross validations error is high for when k is equals to low as well as when k is equals to high. Just our cross validations error will be look like that. Taken here another color, then high, first initially high, then it will decreased, for some time it is also will be high. Look like that, look like, not appropriately, just assume, look like that. First it is increased, and then when we have increasing the value, after some time it is decreased, then again we have increased, then again this thing is decreased, this increased value. So this kind of graph in generally we have. So this is called the cross validation error. This is called the cross validation error. Okay, so this region, the regions when this regions is actual called our overfit models, when actual k is equals to low, these regions, this regions example called the overfit region, and this region actually this type, this region is actually called the underfit region. This kind of when k value is large. So what will get? So this region is called the overfit region, and this region is called the underfit region. We got underfit region. So what we'll see, if you just see this thing error perspectives. So in these regions, what we'll get? In these regions, our cross validations error is high. Here our cross validations error is high, and in overfit regions our training error is low. Training error is low. But in these regions, but in underfit regions, what we'll see? Underfit regions, we have seen that our cross validations error is high, as well as our training errors is also high. Our train error is also high. Both the errors is high in this region. Okay, I think this concept is clear. Enter the perfect, we got the perfect k in the middle of this. when our approximately equal, when this thing is approximately equal, just I am taking here another color, when this thing, this color, the deep blue color, if you see these regions, actually a well filled region, this region is actually called a well filled regions, this region is called a well filled regions. Means in these regions, if you see in these regions our cross validation error approximate equal to our training error. Means in these regions our cross validation error is approximate equals to our training error. These things actually are a well fed regions. So in such regions we call that our model is well fed. So I think even understands how numerically, how by simple comparing the error term training error and cross validation error, if we just see the training error and cross validation error, you can easily determine in which regions our model is overfitting and in which regions our model is actual underfitting. I think you understand the concept. So the relationships between the cross validation error and training error, in actual which regions this model will fall overfit and actual which regions this model fall underfit. I think this thing is clear all of you. Suppose let's take here our actual k is equals to, suppose let's take our here k is equals to 5. So let's take k is equals to 5 here. Let's take for something. So for some time it scales. Let's take. So what we'll get? We get that when k is equals to, taken here another color, then it will be better. When k is equals to 1, then we have see our model is actually overfit model. And when k is equals to n, you see that our model is underfit model. And when k is approximately equals to 5, then we have see that our model is well fit in these regions. And we have see the relationships between cross validation error and training error for age regions. So just if you just summarize this thing in language, what we will get till now what we have seen, we have seen that our training error, if our training error is high and our cross validations error is also high, then what? Then in these regions, this means our model is underfit. Then this model is underfit. And also we have seen that if our training error is low and our cross validation error is high, then we will see this is actually a overfit model. Means this region, and we have seen when our training error is approximate equals to cross validation error, then in such scenario we called our model is well fit. Means this regions. I think the concept, main primary concept is clear. How to determine actually by simple accuracy or finding simple error term, we how to actually we find our model is actual overfitting and underfitting by simple see the error term. I think this concept is clear. If you have any problem, please I request you please revisit this. I think I have clearly elaborated this thing. And although if you have any problem, please revisit these lectures. And if you have any problem, please comment below. Then again I will make another lectures on these topics. Okay, I think today's mottos of this lecture is I will give my clarifications all of you. Okay, although if you have problem, please comment below. Then I will try to give my best answer as simple as possible. Okay.